Manufacture of nitric acid by Ostwald's process. The step 1, first chamber, catalytic chamber. Conversion, catalytic oxidation of ammonia to nitric oxide. 4NH3 plus 5O2 in the presence of platinum at a temperature of 700 to 800 degrees Celsius, 4NO plus 6H2O plus 21.5 kilocalories. The reactants, pure dry ammonia, dry air. The ratio of reactants, ammonia is to air 1:10 by volume. Catalyst, platinum gauze. Temperature 700 to 800 degrees Celsius maintained electrically. Nature of reaction, exothermic. Products, nitric oxide NO, steam H2O. Conversion ratio, 95% NH3 converts to nitric oxide NO, remaining burnt to nitrogen and steam. Step 2, chamber, oxidation chamber. Conversion, oxidation of nitric oxide NO to nitrogen dioxide NO2. 2NO plus O2 at 50 degrees Celsius gives 2NO2. Temperature around 50 degrees Celsius. The step 3, the chamber is absorption tower. Conversion, nitrogen dioxide to nitric acid by absorption in water in the presence of acid. 4NO2 plus 2H2O plus O2 gives rise to 4HNO3. Temperature, ordinary temperatures. Manufacture of nitric acid by BIRKLAND and EYDE process. Let us see the manufacture of nitric acid in the BIRKLAND and EYDE process. Here we have an electric arc furnace which is fitted with two electrodes through which electricity is passed. Through this inlet, air is sent inside. It goes under electric arc discharge, and from there the air is entered into the second chamber, that is the oxidation chamber. From this, the gases are sent into the third one, which is the absorption tower. Again, air is poured from the top, where the acid liquefies and collects at the bottom. Through this outlet, the nitric acid can be collected at regular intervals. In this process, nitric acid is manufactured from the cheap sources of air. Nitrogen and oxygen present in air are made to combine by subjecting them to an electric discharge at 3273 Kelvin. N2 plus O2 gives rise to 2NO minus 43 kilocalories. This reaction is reversible and endothermic. Hence, the reaction is favorable at high temperatures. The nitric oxide NO obtained is quickly cooled and oxidized to nitrogen dioxide by oxygen. The vapors of nitrogen dioxide and oxygen are washed down by water, trickling in absorption tower to form nitric acid. 2NO plus O2 gives rise to 2NO2. 4NO2 plus 2H2O plus O2 gives rise to 4HNO3. Properties of nitric acid. Physical properties of nitric acid. Color, pure acid, that is 98% concentrated, is colorless. Commercial acid, 68% concentrated, is yellowish brown. Odor, suffocating. Taste, sour taste. Physiological nature, non-poisonous, highly corrosive. Density, heavier than water. Pure acids, specific gravity 1.54. Commercial acid specific gravity is 1.42. Solubility, highly soluble in water. Constant boiling mixture, forms a constant boiling mixture with water boiling at 121 degrees Celsius containing 68% of the acid. Boiling point, pure acid 86 degrees Celsius. Freezing point, pure acid freezes to a white solid having melting point of minus 42 degrees Celsius. Nitric acid affects the skin if it accidentally falls on it. Nitric acid has an extremely corrosive action on the skin and causes painful blisters. It combines with the protein of the skin, forming a yellow compound, xanthoprotic acid, and hence stains the skin yellow. Distillation or boiling cannot be used concentrated nitric acid beyond a certain concentration. An aqueous solution of nitric acid forms a constant boiling mixture boiling at 121 degrees Celsius and contains 68% of the acid. A constant boiling mixture is one which boils without change in composition. Hence, on boiling, the above mixture evolves out the vapors of both acid and water in the same proportion as in the liquid. The dilute nitric acid cannot be concentrated beyond 68% by boiling. Further concentration of the acid is only possible by distillation of acid under reduced pressure in the presence of concentrated sulfuric acid. This gives nitric acid of about 98% purity. 98% acid is commonly known as fuming nitric acid. Chemical properties of nitric acid. The first one, nitric acid stability. Pure nitric acid is unstable and decomposes slightly even at ordinary temperature and is even sensitive to light. At higher temperatures, the decomposition is complete, forming reddish brown NO2. Hence, pure HNO3 kept in plain glass bottles turns yellowish brown. 4HNO3 gives rise to 2H2O plus 4NO2 plus O2. Nitric acid as an acid in the dilute form. Dilute nitric acid is monobasic and exhibits acidic nature. The monobasic acids dissociate in aqueous solution to produce one hydrogen ion H plus per molecule of the acid. Nitric acid dissociate in aqueous solution to produce one hydrogen ion H plus per molecule of the acid, hence monobasic. The equation HNO3 gives rise to H plus NO3 minus. H plus H2O gives rise to H3O plus, that is hydronium ion. How to show the acidic nature? The presence of hydrogen ion H plus imparts acidic properties to an aqueous solution of nitric acid. The general reactions of dilute acids are acids plus base gives rise to salt plus water only. Similarly, acid plus carbonate gives salt plus water plus carbon dioxide. Then acid plus bicarbonate gives salt plus water plus carbon dioxide. Reactions of dilute nitric acid, acidic properties of its solution. The first one with a metallic oxide. ZnO amphoteric plus 2HNO3 gives rise to ZnNO3 taken twice plus H2O. The second is metallic hydroxide. NaOH alkali plus HNO3 gives rise to NaNO3 plus H2O. Next one, carbonate. CaCO3 plus 2HNO3 gives rise to CaNO3 taken twice plus H2O plus CO2. With bicarbonate, NaHCO3 plus HNO3 gives rise to NaNO3 plus H2O plus CO2. Nitric acid in the oxidizing nature. Nitric acid is a strong oxidizing agent. The oxidizing property of nitric acid is based on the fact that when nitric acid undergoes decomposition, it yields nascent oxygen and acts readily as an acceptor of electrons. 2HNO3 concentrated gives rise to H2O plus 2NO2 plus O. 2HNO3 it's moderately concentrated gives rise to H2O plus 2NO plus 3O. The nascent oxygen oxidizes nonmetals, metals, inorganic and organic compounds. Nitric acid itself undergoes reduction in a number of ways and hence a number of reduction products NO, NO2, N2O etc. are formed depending on the acid, concentration and the temperature of the reaction. With nonmetals, concentrated nitric acid liberates nitrogen dioxide NO2. Carbon C, which is a nonmetal, plus 4HNO3 gives rise to CO2 plus 2H2O plus 4NO2, that is nitrogen dioxide. With metals, cold dilute nitric acid, that is 1% acid, liberates hydrogen. Magnesium Mg, that is a metal with 2HNO3 gives rise to Mg NO3 taken twice plus H2. Hydrogen is generally not liberated when dilute nitric acid reacts with metals. Nitric acid is powerful oxidizing agent and the nascent oxygen formed on decomposition oxidizes the hydrogen to water. Magnesium and manganese, however, react with very dilute nitric acid at low temperatures to liberate hydrogen, since the oxidizing action of the acid is much reduced due to dilution. Nitric acid oxidizing nature. Dilute nitric acid in the cold condition liberates nitric oxide NO. Copper with some metal 3Cu plus 8HNO3 dilute gives rise to 3CuNO3 taken twice plus 4H2O plus 2NO. Similarly, concentrated nitric acid hot or dilute nitric acid liberates nitrogen dioxide. Copper with some metal Cu plus 4HNO3 concentrated gives CuNO3 taken twice plus 2H2O plus 2NO2. The passivity or inertness is exhibited by certain metals under condition in which chemical activity is expected. Iron is rendered passive due to the formation of a tin oxide coating on the surface of the metal, which prevents further reaction. If oxide layer is removed mechanically or chemically, the metal becomes active again.